Good morning, all of you.
Good morning, sir.
Good morning, sir. Good morning, sir.
So now I could see 10 students. So let us wait a few minutes for others to join. Okay, so now we have a critical mass 17. I could see 17 here, and just at the beginning, please turn on your video for a few seconds. Okay, Srija, Chirantan, Shoham, Sramona, Shamrat, okay, Devangana, Aniruddha, Shomojit, Amit Rakhar, Ritik, could you please turn on your video? Okay. Ritik, can you hear me? Ritik Majumdar. Okay, Shagnik. Okay. Okay, fine. So now you may switch off the videos and let us start the class. So in the last class, we were talking about the classification of the atmosphere on the basis of temperature as well as composition. So there we have seen that contrary to the common sense logic, temperature does not increase linearly with height. Instead, there is some kind of a quasi-periodic variation in temperature before within the first, say, 100 to 110 kilometers above the surface of the Earth, above which it increases continuously. Now, today we will talk about the classification on the basis of ionization, and this property of ionization is indeed one of the most important when it comes to long distance radio wave propagation. The ionized part of the atmosphere, this is named ionosphere, and it extends typically from about 50 to 60 kilometers above the surface of the Earth, and the major concentration of ionization is limited to within the first, say, 700 to 1000 kilometers. And however, I must say that traces of ionization that could also be found at altitudes as high as like 40,000 kilometers above the surface of Earth. Now, basically, this ionization is formed by the incident solar UV radiation. When it falls on the neutral gas molecules, as you could see over here, then it produces ions and electrons. And on this background of ionization, there are superposed, a number of different maxima, as we will see. So, if you look at the variation of, say, electron density as a function of height above the surface of the Earth, then during the daytime, the variation is something like this, that it starts from roughly about, say, 60 kilometers, and you have maxima occurring somewhere around, say, 80 to 85 kilometers. And then once again it starts to build up. There is a second maxima somewhere around, say, 110 kilometers, and thereafter once again it starts to build up and reaches heights of around say 180 kilometer, and finally the highest value of ionization is obtained at altitudes of around say 300 kilometer. Okay, the corresponding values of electron density, as you could see from here, are like 10 to the power 4 per cc for the lowest peak, then about 10 to the power 5 for the next higher one, 10 to the power 6, and 5 into 10 to the power 6. This is typically the values of electron density that you get at different heights above the surface of Earth. And above typically 300 or 350 kilometer, the values, they fall off. So these layers were discovered more or less around, starting from around the early 1920s. So it's like 100 years back, and they were named according to the different English alphabets. Okay, so people started with the lowest layer, they named the lowest layer D, then the next higher one as E region. So as you could see, the D layer starts from around 60 kilometer, and then the E layer that starts from somewhere around 90, and the F layer is once again bifurcated. There are two regions differentiated on the basis of their ionization. One is the F1 and the other is known as F2. This is during the daytime. Now, one question that usually comes to the mind is that if these layers have to be named after the English alphabets, then why start from D? Why not from A? So the idea at that time was that, around the 1930s and 40s, the idea was that gradually more layers of lower density will be discovered, and for that they had set aside the first three letters of the English alphabet, A, B, and C. Okay, but actually that did not happen, and these are the layers that are officially recognized by the scientific community for the different ionized regions of the atmosphere. Now, one of the interesting things that we should note from this figure is that the variation of electron density within each layer is some kind of exponential. That means as if in each layer the electron density starts to increase exponentially, reaches a maximum and halts. Then again in the next higher layer it once again starts to build up, reaches the maximum and stops. Then again in the next higher layer, and so on. So this actually tells us intuitively that the variation of the neutral particles in the atmosphere that we had discussed in one of the earlier classes. So where we have seen this n, I think it was here, yes, that is your n is equal to n naught e to the power minus small h by capital H. That means the neutral particle density we had derived is it follows some kind of an exponential variation with height. So that may also be applicable to some extent for the ionized part. Okay, the earlier relation was for the electrically neutral regions of the atmosphere, and while this is the ionized part, electrically ionized part of the atmosphere. Then again, during the night time, we find that the variations is much more simpler, in the sense that you do not have so many layers to talk about. Basically, you have a layer which starts with a peak of around 10 to the power 4 to 10 to the power 5, and then you have a maxima occurring near about the same height, or sometimes a little lower. So basically, this ionization present, or electrons present in the atmosphere, is generated by or produced by the solar UV radiation falling on the neutral gas molecules. Now we will see progressively that there are different wavelengths of radiation emitted by the sun, and depending on the wavelength which is incident on a particular layer, you have different layers being formed, as we could see from here, the D region, the E, and the F. Okay, so if we consider that effect of these different layers on long distance radio wave communication, then we will see that they are extremely important, and they practically sustain long distance radio wave propagation, whether it is daytime or nighttime. So the lowest layer in this ionized atmosphere is known as the D region, as we had seen. It roughly extends from about 60 to 90 kilometers, as we could see from here. And this is mainly present during the daytime, because as you could see from here, that at night time, the D region is no longer present. Okay. So the effect of this D region is that it causes attenuation of high frequency radio waves. That means the radio waves that typically propagate, if we look at the high frequency band from here, this is typically from about 3 to 30 megahertz, and the effect of this D region is to cause attenuation of this high frequency radio waves. So this particular layer, it does not exist during the night time, and that possibly explains why, when we look at the communication, long distance communication using high frequencies or short wave, okay, যারা আগেকার দিনে রেডিওতে ইন্টারন্যাশনাল রেডিও চ্যানেলগুলো শুনতেন, যেমন ফর এক্সাম্পল BBC, okay, for example, they had this experience that during the evening hours and night time, the quality of the signal was better. Now, the major reason behind that was that the disappearance of the D layer after sunset. So after sunset, local sunset, the D region does not exist, and so the influence of this layer in attenuating the high frequency signals, that is also absent at such times. In fact, in our younger days, we still remember that we did not have this kind of dish TV and things like that at our home. And whenever Test cricket was being played in England, we used to tune in to the radio on BBC. And usually the matches in England, Test matches, they used to start from around our local noon time, say around 3 p.m. afternoon, and continue till maybe 10 or 11 at night. So we had this experience also that during the initial part, say from about till about 5 or 6 in the evening, the signal quality was not that good. But with the progress of the evening and the night, gradually the quality improved. So that was mainly caused by the disappearance of the D region after the local sunset. Next, if we come to this E region, then the E region is mostly prominent during the daytime, that is from sunrise to sunset. But after sunset, this ionization also in this layer, it decreases rapidly. Okay. Now, the signatures of all these layers are found on some kind of a device, instrument, which is known as an ionosonde. And the output of those ionosondes generate some kind of graphs or plots of this height variation. So those graphs or plots are known as ionograms. We will talk about ionosondes later in the course. So the E region, it is mostly present during the daytime, as you could see over here, that it has got significant amount of contribution in terms of the electron density. But after a sunset, it gradually disappears. Sometimes actually, there are some sporadic layers which are still present in the E layer, E region heights, which is referred to as sporadic E. Sporadic means এটা রোজ হবে না. Okay, it will not follow any definite pattern or rule. This will happen randomly, more or less randomly, and that is why this layer is also referred to as sporadic E. So this layer is likely to occur randomly on certain evenings after sunset. And this layer is of course some kind of a very thin layer. Then when we come to the F region, which contributes to the highest amount of ionization in this ionized part of the atmosphere, so there this F region is sometimes bifurcated into F1 and F2, as we had seen. The F1 region or the layer typically extends from about 130 to about 200 or 210 kilometer, while the F2 layer, it extends from about 210 to about 400 or 350 kilometer. These heights, they are not fixed. Okay, because these regions are generated through completely natural processes. Humans cannot influence or change or modify these production of electrons or ions in the atmosphere. So that is why these corresponding heights, they are also kind of not absolutely fixed. On a certain day you could have the peak of the ionization density occurring around say 350 kilometer. On another day, it could be around 400 kilometers. Now, the important thing is that because we have already mentioned that the incident solar UV radiation is the primary source which causes this, electrons or ions to be formed, to be produced. So the natural question should be that after sunset, when the source of this ionization is not present, then the electron density or ionization density should fall to 0. But surprisingly, that is not the case. That is, even after sunset, we find that there are ionization present in the atmosphere, although the levels may not be that high as during the daytime, as we could see from here, but they are enough to sustain long distance communication at night. So that is why it is mentioned that long distance radio propagation at night that is sustained by the F layer. Okay. Now, what is the process by which that is happening? That is something that we will discuss when we consider the propagation of radio waves through different kinds of fields. Okay, just a minute. So this ionization density, this is also a function of the time of the day. We had seen in this diagram the variation of this electron or ionization density as a function of height. In addition, it is also a function of time of the day and also the region in the world where you are located. That means if you are located in the equatorial region like India, say for example, then your values of ionization or electron density is one of the highest in the world. There are reasons behind that, we will discuss that. While if you are in the mid latitudes, say for example in the US or Europe, then your values of electron or ionization density, they will be not that high. Okay. Now coming to the variation of this ionization or electron density as a function of time of the day, this starts to build up after sunrise and reaches a diurnal maximum value around say 13 to 14 local time. Okay, when we talk about time, there are usually 2 or 3 different definitions of time that we are familiar with. One of them is of course the Indian Standard Time. It is the time at the meridian. Do you know how the Indian Standard Time is defined? Anyone?
It's plus 5 hours 30 minutes from Greenwich Meridian. 5 hours 30.
No, every time has got a corresponding longitude or meridian associated with it. Because if you go say 15 degree to the west, then the local time at that place is 1 hour behind because the earth is rotating. On the other hand, if you go 15 degree to the east in longitude, then the local time at that place is like 1 hour ahead.
Yes.
And this calculation is, you could follow it easily. That is, in 24 hours, Earth moves through 360 degrees. So basically, in about 1 hour, it moves through 15 degrees.
15 degrees.
So the Indian Standard Time is specified with respect to the longitude of 82.5 degree, which passes through Allahabad. So that is one definition of time with which we are familiar. Secondly, we also know about the Greenwich Mean Time or the Universal Time. It is the time at 0 degree east, which passes through Greenwich near London. So with respect to that, what you said is correct, that the Indian Standard Time is 5 hours 30 minutes ahead. There is a third definition of time, which is like the time at a particular meridian. So that time is known as the local time, the time at your meridian. So if you simply follow the rule and try to calculate, then suppose if I tell you that the longitude of Kolkata is 88.5 degree east. Okay. So can you tell me what will be the local time at Kolkata with respect to the UT? That is how much it is ahead or behind UT.
So it is 5 hours for 54 minutes ahead
5 hours?
54 minutes?
Hello?
So 5 hours 54 minutes?
It is 5 hours 54 minutes, right?
Yes, sir.
So how did you get this value?
So I divided by 15 and then got 5.9 and then 0.9 I multiplied with 60 to get 54.
Right. So you could see that while the Indian Standard Time, so if you say that IST, that is actually UT plus, please do that same calculation for 82.5 degree, 82.5.
Yes, it is 5.5, so 5 hours 30 minutes.
So that will be like 82.5 divided by 15.
Yeah, so 5.5.
So it is like 5.5. So that is, if we follow the same format, it will be 5 hours 30 minutes. So from here you could understand that most of the effects that we will be talking about, it is always better to use the local time than the Indian Standard Time, because the local time at Kolkata will be different from the Indian Standard Time, as well as the local time at, say, Ahmedabad, that will also be different from the Indian Standard Time. So the interesting thing is that because the main source of this electron or ionization density is the solar UV radiation, so mathematically we should expect that, or logically we should expect that when that source of ionization is no longer there after sunset, then the ionization should fall to zero. But actually it does not happen that way. It is almost like the discharging of a RC circuit or a capacitor, you could say, which is very prolonged. The charging up takes place quite rapidly, after local sunrise, you could reach the maximum, the diurnal maximum value around say 13 to 14 local time, but actually after that it starts to decrease and does not become zero at any point of time. There is often a secondary maxima around say 21 hours local time, and then in the post midnight hours it reaches very low values. Okay, so what we have to remember over here is that although logically the source of ionization is no longer present after sunset, but still the ionization density that continues to exist, and the proof that it does exist even after local sunset is that we are able to perform long distance radio communication at night. Had the F layer or any of the other layers been completely absent at night, then this long distance propagation would not have been possible. Now, there are some theories which try to explain this, theory of how these electrons are produced. So, the standard theory which is universally used and considered is what is known as the Chapman theory of electron production. So basically, before going into the detailed mathematics of that theory, which explains how the electrons are produced, if we consider, say for example, the three main components in this development of ionization. So you have the intensity of the ionizing radiation from the sun, and that intensity, once again, you should understand that that is also a function of the angle at which it is incident. Okay, that means when we say that the ionization density is a function of time of the day, then you may ask this question that fine, it means that the solar radiation of a particular wavelength is responsible for ionizing certain species of neutral molecules. So if the wavelength is the same, then why should there be a change in the amount of ionization as a function of time of the day? The whole day it should remain at the same level. The answer to that lies in the fact that this intensity of this solar ionizing radiation, that is also a function of the angle at which it is incident on a particular layer. That means this is our common sense understanding that at the time of sunrise, the sun is low on the horizon. So the ionizing radiation from the sun, that falls at a very small angle. The zenith angle is very large, of course. Zenith is just the complementary of the elevation angle. So the elevation angle is very small at the time of sunrise. Then with the progress of the day, the sun gradually comes nearly overhead. So the angle, the elevation angle, that increases and it reaches a maximum around the noon time, and then once again starts to decrease and has very low values of elevation at the time of sunset. So the intensity of this ionizing radiation is one of the important factors to consider. Second is the number density of this ionizable molecules. So that means that from the variation of these atmospheric constituents as a function of height, what we have seen so far is that essentially there is some kind of an exponential variation with height. That means that the values of these ionizable molecule number density is high at the lower altitudes, and as you go to higher and higher altitudes, that number density decreases. So from the perspective of the incident radiation, the intensity of this ionizing radiation is very high at high altitudes, and because of the absorption of some of this incident radiation by the atmosphere, by the time this radiation reaches the lower heights of the atmosphere, its intensity has decreased. So the intensity of this ionizing radiation is very high at high altitudes and low at heights near the surface of the Earth. But the number density of ionizable molecules follows just the reverse variability. That is, it is small at high altitudes and high at low altitudes. So as a result, you could see that it is this interaction between the ionizing radiation and the ionizable molecules that determines what will be the rate of this electron production. So at the top, intensity is high, but then there are not enough ionizable molecules. So the rate of electron production is not very high at high altitudes. Then again, at the lower heights, number of ionizable molecules is large, but then the ionizing radiation that has become weak while traversing this upper heights of the atmosphere. So here again, once again, the rate of this electron production will be low. So we will expect that somewhere in between the rate of this electron production that should maximize. Okay, so this is some kind of a intuitive understanding based on physics. We will try to develop some mathematical relations or study some mathematical equations and try to understand that how we could quantify these features, because eventually to the person who is designing a long distance radio communication link, he or she has to know the numbers. Okay, they have to be provided with quantified values. that this will be the amount of ionization at this height, and this will be the altitude at which the rate of electron production will maximize. So this is some kind of a very initial understanding from Chapman theory. Now, when we consider the derivation of this theory, there are some highly simplified assumptions. Okay. At times it may seem that these assumptions, they are extremely simplified to make the calculation easy. Like one of the first assumptions is that the atmosphere is believed to be composed of only one kind of particle, molecule or atom. Okay, that means there is only one species which is present in the atmosphere. That is definitely not the case. Secondly, the ionizing radiation, which is the source of this electron production, that is assumed to be monochromatic. That means that it comes almost at a single frequency, single wavelength. So that again is definitely not the case in practice. The third assumption is that the atmosphere is assumed to be isothermal. If you remember and go back to this derivation of the neutral particle density, you will find that there we had made that assumption that in an isothermal atmosphere, because T is a constant, so from this relation we had obtained dP by T will be dN upon n. But to actually expect that there is no temperature variation in the atmosphere, because now we are familiar with this figure, which shows there is very definitely very much a variation of the temperature as a function of height. So that also it appears to be highly simplistic. Then the atmosphere is assumed to be horizontally stratified. That means the curvature of the Earth is not taken into account. So finally, of course, we will see that in spite of all these some kind of highly simplistic assumptions, Chapman theory, it does give us values of this electron production rate, which actually from measurements are found to be nearly correct. There are some minor errors here and there, but overall we will see that the values of this electron production rate as well as the electron density, which is predicted by Chapman theory, that is more or less what we actually find from experimental measurements. I think I will stop here today, because once I go into the derivation, I cannot divide that into two classes. So let me have your attendance now, and we will continue with this derivation in the next class. Shubhodip Mukherjee.
Yes, sir.
Moushumi Shah,
Yes, sir.
Srija Chakraborty.
Present, sir.
Srija?
Present, sir.
Okay. Ramona Majumdar.
Present, sir.
Yes. Moushumi Mondol. Moushumi Mondol. Okay. Shamrat Malakar.
Present, sir.
Debraj Dash.
Yes, sir.
Soumojit Bashak.
Present, sir.
Devangana Bashak.
Present, sir. Hello,
Arun
sir.
Kumar Hari.
Yes, sir.
Shayani Roy. Shoham Paul. Chirantan Ganguly.
Present, sir.
Aniruddha Mondol.
Present, sir.
Amitrakhar Sannal.
Present, sir.
So this
Present,
will be your
sir.
first class, right?
Sir, my attendance was missed.
Yes.
Sir, my attendance was missed. 411 Shagnik Naik.
411.
Yes, sir.
Okay. Thanks.
Sir, 437 Shreyashree Roy.
437.
Yes, sir.
Yeah, I'm coming to it. Othikrit Gupta. Shreyashree Roy is present, right?
Yes, sir.
Ritik Majumdar. Suprabhat Bhattacharjee.
Present, sir.
Shayan Datta. Okay. So thank you, and we will meet next week. And stay safe.
Thank
Okay.
you. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.